In this lesson, we're going to solve trig identities. We're going to prove trig identities, to be more precise. Because proving a trig identity means that you're going to show that a statement is true for all values of the variable. So not specific ones, not just a particular one. So we can't just substitute something into an equation and see if it balances, because all that shows is that it's true for that particular value. But we want to see that it's true for all values. Now there's some important ones here that we already should know from previous math courses, in particular the quotient identity. Tan theta equals sine theta over cos theta. We're going to use that one a lot. And the reciprocal of that is cotangent equals cos theta over sine theta. We have the reciprocal identities over here on the right. We should know those ones. We know cosecant equals 1 over sine theta and so on. We might use those occasionally. Pythagorean identity is the other big one. Sine squared theta plus cos squared theta equals 1. And then rearrangements such as this or this are other versions of it. But the ones I've done in red are the basic ones that we need to memorize. Those are the ones we're going to keep going back to again and again. And then, of course, like I said, the ones I've done in blue are just variations of it, which we should be able to work out. As well, there's the compound and double angle formulas that we've learned. So there's all kinds of things that we can use for proving trig identities. Before we jump into using quotient identity or Pythagorean identity, let's go back to prove where the quotient identity comes from. So, I'm going to draw a Cartesian plane here. And let's just draw a terminal arm on it. So remember, if we've got a terminal arm and it's got this point P, X, Y on the terminal arm, then we can create a right triangle by dropping a vertical line down to the x-axis. That means that this side length here is just going to be equal in length to whatever the y-coordinate is. This side length is going to be equal in length to whatever the x-coordinate is. And the hypotenuse is going to be the radius. We call that r because we could make a circle by just rotating that terminal arm around 2 pi radians, or 360 degrees. And that would be the radius. So we've used the letters x, y, and r before. Let's show how we can use them, though, to prove that tan theta equals sine theta over cos theta. So our technique is always to work on one side or the other. So let's work on the left side. I'll use ls to represent left side, although I won't put an equal sign there. What I will say, though, is that tan theta, using this sketch, is going to just be y over x, right? Opposite over adjacent. So left side boils down to y over x. The right side, which was sine theta over cos theta, could be rewritten as sine theta is y over r, opposite over hypotenuse, and cos theta could be rewritten as x over r, so sine theta divided by cos theta is the same as y over r divided by x over r. And if I simplify that, we know that when we divide fractions, we can invert the second fraction, turn it upside down, and multiply. So x over r becomes r over x. And if I multiply, the r's cancel out, and I'm left with y over x. And that is the same as what tan theta equals. So I've just proved, using first principles, that the left side equals the right side. And I didn't use any specific values. I just used variables x, y, r. And so that proves that this is going to be true for any values that I care to stick in there. Usually I just finish up by saying this equals the left side, and so on. Same idea for the Pythagorean identity. If I go to first principles, for the left side, I can take sine squared theta plus cos squared theta. And again, I know that sine theta is just y over r, so I could do y over r squared. And I know that cos theta is just x over r, so I could do x over r squared. If I take off the brackets, then what I end up with is y squared over r squared plus x squared over r squared. And I'm adding them together, of course, so that means that since there's a common denominator, I can actually just bring the two numerators together, y squared plus x squared over r squared. But we also know, using the Pythagorean theorem, if we go back to this triangle here, this is a right triangle. So we know that in this triangle, r squared is equal to x squared plus y squared, and therefore x squared plus y squared, or as I've got it written, y squared plus x squared, order doesn't matter, must be equal to r squared. So I can replace y squared plus x squared with r squared. So now I've got r squared over r squared. Anything divided by itself equals 1, and we've just shown that sine squared theta plus cos squared theta equals 1. Again, these are first principles. I don't want you to use x, y, and r to solve trig identities in general. Just wanted to show where these ones came from. I would like you from now on, now that we have proven that quotient identity and Pythagorean identity hold true, and that we still have our double angle formulas and our compound angle formulas and everything else, those are definitely we want to use. Here's some tips though. Some of them are rules, some of them are more tips. So rule is we have to separate the left side and the right side. We can't just rearrange like we're solving an equation, okay? We can't do that. We have to work on each side separately. Do start with the more complex side first, because we're always looking to simplify. And so the more complex side obviously gives us more opportunities of things we can simplify. Convert things to sine and cos wherever possible. So if you see a tan, for example, change that to sine over cos. If you see cosecant, change that to 1 over sine. Or if you see secant, change it to 1 over cos. It's easiest if we keep things in terms of sine and cos. Sometimes we're going to need to factor. That'll help us. If we can factor things in certain situations, we'll be able to cancel, just like reducing a rational number. And if we have multiple terms, often we can combine them by getting a common denominator in the fraction and then bringing things together. So those are some general techniques, especially, well, actually, I'm going to cancel what I was just about to say and just jump into an example. Prove the following statements using identities. In other words, prove these identities. So looking at this, let's go through, best approach. I'm going to do the left side or the right side one at a time. And I want to start with the one that looks more complicated. So to me, we got left side. That's more complicated. So 1 minus cos squared theta times cosecant theta. And I want to simplify that down. If I can somehow turn that into a sine theta, my job is done. Well, this 1 minus cos squared theta, I recognize as one version of the Pythagorean identity. If we go back up to the top, 1 minus cos squared theta, there it is. Well, it turns out that 1 minus cos squared theta is just equal to sine squared theta, so I can do a replacement there. So I can replace 1 minus cos squared theta with sine squared theta. And cosecant is a reciprocal, and it's the reciprocal of sine, so I know that cosecant is the same as 1 over sine theta, so I can replace that there. And then I can maybe simplify things a bit. I can think of this as sine squared theta over 1, and I can reduce. Since I'm just multiplying two things together, I can do sine theta goes into itself once, and it goes into sine squared theta 2 times, but it goes in, well, not 2 times, but sine theta times. In other words, I can cancel out the squared on the sine squared theta. So I'm left with sine theta times 1 over 1, which is just simply equal to sine theta, and that equals the right side, and so we've proven it. For the second example, again, the left side certainly looks more complicated to me. I would work on that one. So I'm going to start with 1 plus secant theta over tan theta plus sine theta. And again, if we keep in mind this idea of putting things in terms of sine and cos, then the next step should be pretty obvious. We can change secant into 1 over cos. We can change tan into sine over cos. Now we're going to end up with fractions inside fractions, which is ugly, but sometimes we have to break a few eggs to make an omelet, to use an old saying. We have to make a mess. We have to get messy first sometimes before we can get what we want. So I'll change secant into 1 over cos. I'll change tan into sine over cos, highlighting just to show where things match up. So it does look kind of messy, and my highlighting's not helping any, but what I want to do is I want to get rid of whatever fractions. In fact, there's no fraction. Well, I guess I could think of cosecant theta as 1 over sine theta, but there's certainly not as much fraction stuff going on the right-hand side as on the left. So I definitely want to do something to simplify these fractions. A great way to get to simplify fractions is to bring them all together as much as possible using common denominators. And if I've got fractions divided by fractions, then I can invert and multiply. So let's change the numerator to a common denominator. So since I've already got the 1 over cos theta, it's supposed to be a theta there, 1 over cos theta, then I can change 1 to have a common denominator by writing it as cos theta over cos theta, right? Cos theta over cos theta is equal to 1, as I just highlighted in yellow. And then I'll be able to bring those together as a common denominator. I've already got a common denominator of cos theta on the bottom as well. Or I don't have a common denominator, but I already have a fraction with a denominator of cos theta on the bottom. And so I can change that into a common denominator if I write this sine theta as sine theta times cos theta over cos theta. Again, I'm playing with these a bit just to get a common denominator, because the next step then is in what I've got as the numerator here, I can add them together. I can write cos theta plus 1 over cos theta. That's just the numerator. And in the denominator, I can write sine theta plus sine theta times cos theta over cos theta. Things aren't looking much simpler yet, but we have to have a little bit of faith that if we keep working at it, we'll get to where we want to be, as long as we don't break any of the rules of math. So now I've got a fraction over a fraction. And that puts me in a position that is actually quite nice, because then I can invert and multiply. So I've got cos theta plus 1 over cos theta, all divided by sine theta plus sine theta times cos theta over cos theta. And if I invert the second one and multiply, things might turn out okay. So cos theta plus 1 over cos theta, that is merely the numerator that I just had. And instead of dividing, I'm going to multiply by, I'm going to take this one here and flip it upside down and multiply. So now I'm going to have the cos on top, and I'm going to have sine theta plus sine theta times cos theta. And so that is, this green one is the same as the green one on the bottom, except flipped upside down. What's great about this is that the cos thetas, that should have been a theta, not an x, the cos thetas cancel out. And when I bring it together, I've got just one fraction. I've got cos theta plus 1 over sine theta times sine plus sine theta times cos theta. And I can keep going, right? Now what? Well, I can common factor, right? When things are ugly, think about common factoring, or any kind of factoring. With common factoring, I see on the bottom, I could take out sine theta. If I take that out as my common factor, I'm left with 1 plus cos theta. So I'm going to divide this sine theta and this sine theta. I'm going to take it as a common factor here, leaving 1 plus cos theta. And when I do that, on the top, I've got cos theta plus 1. On the bottom, I've got 1 plus cos theta. That's the same thing. They're just in a different order, right? Those two things I've highlighted in blue are identical, just different order. I can cancel them out. Remember, when we're canceling, they don't become 0. We're really dividing. So I'm left with 1 on the top. And so now I've just got 1 over sine theta. But 1 over sine theta is just equal to cosecant theta, which is what we had on the right to start with. So we have proved this identity. Okay, the last one. Anytime you see something that has, well, that looks like a double angle formula or a compound angle formula, which this certainly does to me, then maybe you should go back and use the double angle or compound angle formulas. So cos x plus pi is one of our compound angle formulas. If we go back a few days, let's see if I can find where I've got it. Compound angle, there it is. We have all those compound angle formulas here. So we've got cos of something plus something. So for today, for this identity, we're going to go with this one. So we want cos A times cos B minus sine A times sine B. All right, go back to the note we're actually working on. So I want that to be the right side, left side. And again, I'll just start with what is on the left side, so cos x plus pi. So we're going to think of x as our a value. We're going to think of pi as our b value. So we have cos x times cos pi minus sine x times sine pi. These, cos pi and sine pi, are just numbers. Again, there's different ways of thinking about it, but when we have simple ones like pi, let's just draw a sketch. Might be the easiest. If I draw, here's a cosine sketch, and one cycle is 2 pi. Here's pi here. So cos pi is going to be -1, since it goes down to -1. So I know that cos pi is -1, so I can simplify that. I've got to leave cos x, so I got a -1 here, minus sine x, I got to leave that. And then sine, let's do that one in blue. When sine pi, or when we have sine pi, that's right here. Well, that's just a value of 0. So sine pi equals 0. Or you could put this in your calculator. Or you could draw it on the Cartesian plane. There's various ways of figuring this out. But however you figure it out, cos pi does equal -1, sine pi does equal 0. And if sine pi equals 0, that means that this whole term goes away, because 0 times anything is 0. All I'm left with is cos x times -1, which is the same as negative cos x, which is what we were asked to prove. And that is it. We're done there. As far as the practice questions go, in this particular one, I don't have the practice questions attached to the note like I normally do, but I do have them. You should find them in OneNote right underneath a separate page, And it looks like this. A little bit blurry. It's just a photocopy, as you can see, but it is there. And there's 13 questions or so. Looks like we're missing a number 9. And the full solutions are below, because especially for trig identities, it's hard to, if you go wrong or if you're stuck, you really need to have those worked solutions to help you go on to the next step. Good luck.